Mm-hmm. Okay. All right. Yes, I will. Okay, hi. Hello, everyone. My name is Robert. I'm with Verlinger and Kromann in Vienna. I will show you a little bit about the plugin Octopus for Grasshopper. It was my master thesis and development during the PhD research. And it was kind of complementary, developed with the development of Caramba, which also happened mainly by Clemens Preisinger and some others also here in Vienna. What I will try to show you today in an example is the generative design of bridges. This is the outcomes of the setup I have created before and the setup to it. So not too big, not too complicated, but creating a number of different design variations in this folded bridge kind of structure, which is supported on the two ends and spanning this gap in between. Before, I wanted to show you some introductory slides to Octopus, especially in the context with Caramba 3D and our Poplar workshop, obviously. So Octopus is kind of a further development of Galapagos, which is a generative design tool. This is the term that is used nowadays mostly for these kind of techniques, where mainly the computer is used for many iterations on a specific parametric setup to improve the design. And the main development compared to Galapagos is that Octopus extended the capabilities to optimize for multiple goals. So it is multi-objective and Galapagos is single objective. Galapagos is the tool that comes with Grasshopper as a standard component, Octopus, as I said, as a plugin. So just to quickly explain, I said it already, generative design is using computational power to improve designs by principles that are borrowed from nature, principles of evolution. I have assembled a little folder with further readings. David Rutten, the creator of Grasshopper and Galapagos, has assembled and written a nice set of articles that gives some background to specific topics. But also I attached my master thesis from 2013, where I created the first version of Octopus. Basically, the algorithms just take a set of numbers and set of parameters of your Grasshopper setup and change them in the beginning randomly and later to a specific pattern, and after some certain statistical probabilities to improve another value, which is some kind of goal function. In this case, the diagonals of the truss, the position of the diagonals in the truss are changed, and the optimization goal is the deflection of the truss. So as I said, my master thesis is attached, but you can also find it in ResearchGate, for instance, and it went under the title Multi-Objective Design Interface. In the office of Verlinger and Kromann, we have been lucky enough to be able to build a set of projects which used these generative design techniques. We have been conducting research projects and also the development of Caramba, obviously now, since about 15 years almost now. This is one of the oldest projects. It's a little railway bridge in Frankfurt in Germany, where these diagonals have been generated just as you have seen before. Or one of the prominent examples, the European Central Bank, also in Frankfurt, where two tower cores are stitched together with kind of also diagonals or stitching steel elements to hold them together, generated with more or less the same technique. So this diagonal stitching is one example application that works pretty well. Another one is the placement of columns. Here is a little project in Liechtenstein from a mixed-use building where the column trees, these prefabricated V and A-shaped columns, have been positioned and tuned with the help of Galapagos back then also. This is another project in Seoul in Korea, the Hyundai Motor Studio, where we actually used Octopus. So a multi-objective generative design tool to place the columns under a huge steel structure which forms the roof. Or a more expressive and artistic project is this pavilion for the Chinese International Architecture Biennale, I think from 2013, with Zaha Hadid architects, where generative design tools were used to optimize or form-find the patterns on the predefined grid shells, the shell shapes basically, and the grid shell pattern was found and optimized with the help of Octopus, amongst other tools. Another project which was in its design very old by Verlinger but was just recently finished is this metro station in Italy, which is typologically a bit similar to what we're going to today. So generated by a folded structure, except that we are going to calculate with surface elements, and this is made up of beam elements. So just briefly a bit of the theory of multi-objective optimization. So I hope single objective optimization is clear. You want to minimize or maximize some goal value of a design. With multi-objective, you just have 2, 3, or more goal values. And they can either be, for multi-objective optimization, the goal values make most sense if they're contradicting. For structural design, this is very often the deflection as one objective, here drawn on the vertical axis, or on the horizontal axis, the cost, which can be governed by the mass of the building or the number of elements or similar things. Then, of course, there can be other goals like lighting conditions or geometric boundary conditions or goals, of course. We'll focus on the structural ones today. The main principle that underlies all multi-objective optimization algorithms is the Pareto Principle, named by Vilfredo Pareto, which was an Italian economist. And besides the most famous thing he did, the 80-20 rule, he also coined the term of Pareto optimality, where you have this set of solutions in a multi-objective setting, and one solution is called Pareto optimal if it cannot be improved for one goal without degrading the other. So it is a setting of limited resources, so to say, and you cannot improve both goals infinitely. This is the interface of Octopus. So you see on the left side the kind of Pareto set of solutions, or the set of solutions in the objective space shown in the default view of Octopus in a 3D Cartesian coordinate system. But there's also another view, especially if you have more than 3 goal values, you want to, we have the size and the color also available in the left default view, but if it's more goal values, you might want to switch to the zigzag view, which draws each objective on one vertical coordinate axis, and each zigzag line is one solution. Just a little example to exemplify, again, the contradicting goals in one structural and one solar objective. So this 4-point supported shell is optimized for maximum stiffness, so least displacement, objective number 1. And objective number 2, the maximum solar gain, shown on the left side, under a given sun path. And on the right side, we see from top to bottom 3 different solutions. The top and the bottom one would be extreme solutions, and the middle one is a trade-off solutions. So if you have multiple objectives which oppose each other, you have extreme solutions for each objective, right? So the top one is the best solution for structural behavior, and the bottom one is the best solution for solar gain, if you wanted to place photovoltaic elements on the shell, for instance. And the thing about multi-objective solution optimization is that you get all kinds of a set of different solutions in between those extremes as well. So the middle one would be a trade-off solution between those two conflicting goals. This is taken from the very brief manual that ships with the download of Octopus, and it shows a typical setup. You have on the very left the parameters, or the so-called genes of the parametric setup or the design. Then you have some parametric mapping function, some definition basically, which produces the output values, the goal values, or the objectives. It's many different names for those things. And then you have Octopus connecting to all of it and creating this feedback loop more or less from the output values, from the goal values, reads those values and changes the input parameters according to these statistical probability functions. The interface of Octopus itself, so this opens up if you double click on the Octopus component, this interface opens up, and we have in the middle the default view of the solution space. Then we have a context menu. If we click on one solution, we have the timeline where you can roll back time more or less by generations of the evolution. We have at 4 we have the control buttons. At 5 we have the algorithm settings and some general settings to the behavior of Octopus. At 6 we have some view settings at the top, so how the view should be scaled, what should be shown in which size, and so on. And at 7 there is a little convergence graph. At 8 we have some values just showing us how long one solution on average needs to evaluate, and some other internal algorithm statistics more or less. Point 9, we have the value distribution of the parameters as a zigzag graph, which is borrowed also from Galapagos. Number 10, we have the list of goal values or objectives. So each row of this table shows one goal value that Octopus is connected to, and there's different settings which we will go through afterwards. And at 11 we have convergence graphs, which show also row by row, each row with one objective, the change in the objective values that Octopus finds. And yeah, if we show the solutions in this 3D solution space, for instance, we know from their position in the 3D space, their relative performance to each other. So in this case, the distance, I can't read up dimension number 3. No, it's just 2-dimensional actually. So the height and the distance we can see from the position in the coordinate system, but we don't know anything about their aesthetics or their appearance. And this is approached in Octopus by the ability to supply meshes to the component. If you supply one mesh per solution, you can show, or it shows, instead of the little cubes, it shows the actual 3D models in the solution, placed in the solution space, in the performance space. Yeah. So what we're looking at today are 3 different, just quickly, when it comes to structural optimizations, we have 3 different typical optimization goals, for instance, that we often use. One is the most obvious. You want to minimize the maximum displacement of a structure. If it doesn't deform very much under its loads, it means it has a high stiffness, which typically is desirable. So, for instance, if you have a flat sheet of paper, you have the supports on one side and you load it with some external load on the other side, it's very weak. It just bends downwards. If you fold it upwards, it gains a lot of stiffness. And this kind of shape optimization is more or less intuitive in this case, but it could also be found by Octopus, for instance. Yeah, I'm not going to go into this. These are some force lines or stress lines that you can plot on shells. Then the second typical optimization goal is to lower the mass of a structure, which means saving material, which typically corresponds to the cost. It lowers the cost of a structure, or it makes the structure more elegant. So this is also a second goal that is usually a good opponent also to the high stiffness goal. So if you want to have a high stiffness and low displacement of a structure, you can just achieve that with a high mass. But if you also want the mass to be very low, these two goals are conflicting. So these are just some examples of the cross-section optimization you could use for that. But I'm just going to switch to the third typical optimization goal, a high natural frequency, which is a bit of an advanced topic. It's not just the deformation of a structure under some load, but it is every object has a number of natural frequencies where it resonates in different vibration shapes, right? So exemplified on a guitar string that just goes from point A to point B, there would be the lowest vibration mode it's not even shown here for some reason. It's just the one where it goes from one side to the other. And this is the lowest frequency it can get. And the second one is the second harmonic. Basically, it has two bumps up and down. The third one goes 3 times up and down. And there are many numbers of these vibration modes. And by making the lowest vibration mode as highly pitched as possible, so to have a frequency as high as possible, you make it at the same time stiffer, without having to apply external loads, which can be very handy. So these 3 optimization goals we will use in the example I will show you now. So we've seen this before already. This is what we're going to produce, or some of these, with this setup, and I'm just going to start fresh. So the first step is the definition of support points. I'm just going to draw 4 points in X, Y, Z. We have here, I'm just going to do it the exact same way. In the origin at 0, 0, 0 position, then at 20, the bridge is going to span 20 meters. And then we have one at 4 meters. Sorry, I was mistaken. The bridge is, we're going to draw it symmetrically around the origin. 1 point at plus 24, 1 point at plus 20 minus 4, and the same with minus 20 meters in X direction. So we have here 40 meters span of the bridge and 8 meters width. These 4 points I'm going to reference with 4 point containers. I'm using 4 separate point containers because I want to be able to set the properties of each support separately, and that's just easiest if I reference them and treat them one by one. Since it's just 4 points, it doesn't really matter. These are going to be our 4 support points, and I'm leaving it like this for now. And the main technique how we are going to produce this bridge design is by using a Delaunay triangulation mesh on a set of points we generate. So these 4 points are always there, always will be given, the 4 support points, and we're going to create 4 other points which we parameterize in their position and then mirror them 2 times along the longitudinal and the transversal middle axis of the bridge. So we have kind of a symmetric design output, which makes a lot of sense for a bridge. So these kind of things always make sense if you know some of these a priori symmetry conditions, for instance. It is very helpful, because always with optimization, if you know something to be inherent in the design, or you could just bottom up encode it. So the optimization algorithm has an easier time figuring out good solutions. So sorry, what I've done now is I'm creating a gene pool. This also comes with Grasshopper. It's in the parameters utils tab. So we have here the Galapagos component that comes with Grasshopper, and made for this kind of application, more or less, the gene pool component, which is basically nothing more than a set of number sliders in one component. And when double clicking it, I can change its parameters. I'm going to have 4 gene counts, 4 number sliders. I'm increasing the decimal points to the maximum of 6, and I'm setting the minimum to 0 and the maximum to 20. This is going to be our x coordinate for each of the 4 points. And I can right click on it and say randomize, and it randomizes the slider positions. I copy this 2 times. For the second one, it's going to be our y coordinate. I'm going to set the maximum to 4. And for the z coordinate, I'm setting the maximum to 6 meters. After that, I assemble points with the construct point component, x, y, z. It's going to give 1 point, which is in the vector and point tab of Grasshopper. Just connect those outputs to the point input, and then I can randomize all of those values, and it creates this set of 4 points. Now what I want to do is to mirror those 4 points along the long axis of the bridge. So this one, and this one. So these are going to be the symmetry axis, and I just use the mirror component in Grasshopper for this. One time I want to mirror around let's see, the YZ axis. I just take the YZ plane as the plane input here, and then so I have mirrored that here already, and then I mirror another time around the XZ plane, and I want to mirror both the original and the mirrored points again. And then in one point container, I'm just going to connect all the different points. So I have this set of 16 points now from the 4 points I created initially. All right, and this is the design input basically. I'm going to save this. Yeah, that's important. If you work with generative design tools like Galapagos or Octopus, it is very advisable to save, especially when you run the algorithms, because as I said, it depends on a huge number of different tries of the setup, and it is not unlikely that your Rhino Grasshopper session will crash during the optimization, just because you have not, because maybe Caramba crashes or Octopus crashes, or just some other bug in the exploitation of the design space through the algorithm comes up. So these are our generative points, sorry, and these are our fixed support points. We're putting them together and create a Delaunay mesh from them. The Delaunay meshing component also comes with Grasshopper by default. It's in the mesh and triangulation tab. There are 2 components with the Delaunay algorithm. One just gives you the edges and one gives you the mesh. We're going to take the mesh one, and we're taking all the support points, and then when we have fed in 3 points already, we see it creates this triangulation pattern. And I'm going to feed in the other generated points as well. And right now, actually, we have created an interesting structure by chance automatically. So maybe it pays off to look at it even. Yeah, it looks kind of like an arch bridge already. Maybe I want to save that for later just because. But basically, it was just a random design right now, obviously. I'm going to flatten those points just to make sure. What I'm doing now is I unweld the mesh just because we want an edgy mesh, and the unweld command makes sure the mesh is like the display of the mesh is not tried to look smooth with the unweld angle of 0 degrees. So I'm gonna bake this for comparison, and you're going to see the difference. So here, it assumes some of the transitions between one mesh face and the other, it wants to be smooth. So it has this kind of weird shading to it. And here, we just tell it, no, you are actually an edgy shape, and we want you to show edgy too. So that just this looks more natural to me. Gotta delete that. So we have the unwelded mesh, and from this we could already create our shell and start with the first Caramba component. But we want to make the mesh finer now. I might explain later if we have time why we do this. For now, I mean, you could also run the Caramba without this refinement of the mesh, but it's a more realistic behavior of the structure if you make the mesh that is analyzed a bit finer. So I'm going to use the split triangles component of Weaverbird. Weaverbird is a third-party plugin by Giulio Placentino. If you don't have it, don't worry, you can also just leave it out. What it does is it subdivides each triangle into sub-triangles a number of times. So here you see how it subdivides the triangles just to make the mesh finer. Okay, so this is our analysis mesh now, and I'm going to use the first Caramba component, mesh to shell, to build up a shell, I'm sorry. And with these shell elements, I've converted the mesh into, I'm going to assemble a model, feed in the elements into the element input, and I have basically my Caramba model already, which I can try to plug into the analysis component, but of course, if I try to analyze this setup, it tells me model cannot be calculated because there are no supports. So we have to still define those 4 outer corner points as our 4 supports. And this is the reason I took them all in one by one. So I can define the support condition in each one. No, just specifically, so a component. I'm going to take the first point as a fixed point in all 3 directions, and for reasons of numerical reasons that are specific to the kind of finite element triangle elements that are used in the implementation of Caramba, it is safer in this kind of setting to also fix the rotation around the z-axis. There could be, under certain circumstances, rotations around the z-axis which are unwanted. So copy this to have 4 of those components and connect each of the points to one of them. And then I'm changing the support conditions. I don't want all of the 4 points to be completely fixed. This would not, like, I want it just to be as fixed such that it doesn't slide around in space. but yeah, I want it to be as loose as possible. This goes into structural mechanics now. So at this point, we're going to fix in all directions. The second point here, we're going to all 4 points will be supported in Z direction. This one will be free in Y direction. This one over here will be free in X direction, and this one will be here, will be free again in X direction and Y direction. So now the structure is supported structurally determinate. And you can also try to make it fixed on all points. Maybe the results will be very similar or even not quite the same. But for now, I'm just making sure this is a nice clean structural setup. And connect all the supports to the support input of the assemble model component. And there we go, we have our structure analyzed already. The component turned from red to gray. And it gives us a valid model output already. Yeah, so right now we could show what the analyzed component gives us is the displacement. We're not having any displacement right now. We haven't defined any loads, but we can look at the structure already. As said, now we can look at the support conditions also. At this point, we have fixed in all 3 directions. This one is just fixed in 2, so we can slide in this in the Y. And the other side can slide in the long direction of the bridge in general. And one of them is fixed in the transverse direction, the other not. So this we can already look at. And now, what I told you before about typical optimization goals, sometimes I could now apply a load and optimize the stiffness of the structure by minimizing this displacement value. But sometimes it's difficult to come up with a load scenario which kind of is universal enough, because the application of loads and its effect on the structure and the bearing behavior to sustain those loads is kind of special in some situations. So it's not that easy sometimes, especially, for instance, if you think of furniture. Of course, if it's a chair, you might want to be able to sit on it, but at the same time, you want to be able to you want it to have certain integrity in general, and you would have to define a number of different load curves. For instance, if someone is rocking the chair or something like that. So a more general approach to optimizing the overall stiffness of a structure is to use the natural vibrations component. Natural vibrations, these are all in the algorithms tab of Caramba. And this gives you, without defining any loads, here we have a deformed structure now already. It gives you the first vibration mode. So this first mode is basically the mode of deformation where the structure is generally the weakest. So if we look at it with the shell view component to have some color on it, we have the displacement like that. And here we have this kind of, I've baked it before, it's this kind of hollow arch bridge. And the mode where it deforms the easiest is this. Yeah? So that makes a lot of sense, at least to me. I think it's quite intuitive. If you imagine it physically, this is the weakest one you have. So by default, it just gives you the lowest frequency mode, and this is the one we're going to optimize for. There is no need to change anything, but of course you can look at higher frequency modes by increasing the number of modes it calculates, and then looking at the vibration mode 1 we have just looked at, this one, vibration mode number 0 or 1 now, the second one. This is the same, but going sideways in a different bit of a different. So basically, and now the free ends, they're having basically the free ends in a lot of cases in this one. And then in the higher modes, now we have a different one. The higher modes will be this end now, flapping up and down. But as said, we just need the lowest one. Yeah, we could try to make this an optimization already. I'm just going to save this solution. If you have a setup like this already, where your design is more or less done, and you're just trying to have different goal values now, you can, in Grasshopper, there's this function to save a state. It saves the state of basically by default all the sliders and gene pools in the setup. You can give it a name. By default here it's the date and time, and I save this. So whenever I change the values here now, so I have a different bridge design, I can say solution restore state from my old state, and it sets these old slider values again. So that's also supported by Octopus, as we might see later. Okay, so I'm trying out, I'm going to start with Galapagos now. We have our design, and let's say we want to increase this vibration behavior just by increasing the natural frequency of the lowest deformation mode. Just going to plug this into a separate number container. Lowest natural frequency, and this is given in hertz. So it's 0.4 hertz. This structure vibrates in. So now the first real generative design part of this tutorial. I placed the Galapagos component. We've seen it already. It's in the parameters and utils tab. Galapagos. Place it somewhere, and then it has two plugs: the genome and the fitness. The fitness is the goal value we want to optimize. So I'm going to connect this to our natural frequency. And the genome are the parameters that we want to change. So I'm going to connect to the 3 gene pools. The second one, I'm holding shift, so it connects to multiple standard Grasshopper UI behavior. I can connect those to those 3 gene pools. And that's it. I can run my first optimization with it and see what bridge design Galapagos for now comes up with. By clicking on the Galapagos component, this window goes up. Octopus works very similar from this perspective. And you see a couple of links to the articles I've been mentioning earlier that I've also printed as PDF and attached to the files for this tutorial. What we want to do with the fitness is maximize. We're going to leave these settings on default for now, which are suitable for many setups. Just what I'm going to do is change between 2 solvers it offers to the simulated annealing solver. The difference that they do, that the 2 solvers do a very similar thing. It's both based on net principles that you find in nature. The left one, the evolutionary solver, is based on principles of evolution, so fitness, selection, mutation, crossover. And this one, the simulated annealing solver, is more inclined towards the analogy of the atoms, the moving atoms of a cooling metal, and the probability of the atoms changing their position and their place. So to say, you can read that, I think, also in the articles. For now, it's enough to know they do similar things. Just the simulated annealing solver sometimes is more better suited to find global solutions, and the evolutionary solver of Galapagos, in my opinion, is better suited to refine certain solutions that you have already. So for this application, we want a more global examination or global take on the optimization, try out as many different designs as possible. So I'm going to use this one. We just hit start the solver, and we see progress. There's some movement in the solver, which tells us, okay, there's something happening. If I look at our CPU usage, if it opens up, we are very busy because Karamba uses 100% of my CPU, because Karamba actually is optimized to use all the cores, and mostly what's happening is the Karamba calculation of the shell. So it's working hard. What we can do to speed up the process quite dramatically actually is to minimize the Rhino and Grasshopper main windows, because you see here it updates for the solutions, it updates the user interface and also the Rhino viewport sometimes at least, depending on the setting here. And this takes quite a lot of time. So if I click minimize in the Rhino window, you see immediately that this progress bar here speeds up quite a bit. So this is always, if you're not really interested anymore on what exactly is going on in the optimization setup, then you can just minimize that and let it run a lot faster. This is the annealing temperature. So the higher the two bumps are, the green and the purple, the other one, the more converged the process is, in a way. Also, you see the number of changes in the goal value here. So this is my natural frequency. We had 0.4 hertz before in the random design. Now we arrived already at 6.5 hertz, which is a lot higher. So I'm just going to maximize the window again and see where it ended up by stopping the solver. I hit OK. And right now, okay, this is the deformed shape. We want to look at the design. It's found as the most stiff. So the lowest natural frequency here is 6.5 hertz, just as we've seen in the optimization window. And here, no, let's not look at this one, but the other mesh. We have found this design. And now with Galapagos, we'll take that as our first generated design with this example. And yeah, this is what we have. And this is one of our one best solution that it found. And that's one of the main reasons why we started with the idea kind of to have a multi-objective solution. So first of all, we just, if we use it in projects, we weren't really sure what's going on inside Galapagos. And we wanted to have a bit more control or insight just in what's going on. But the second is, you optimize for one goal, you get one best solution, and you don't have any choice but to take that one here. So that's one of the good things about multi-objective optimization. You get a range of different solutions that after the optimization is finished, you can still choose from. And that is what we're going to do now. For this now, we are going to define a second goal and the third goal. So the second goal will just be the displacement, minimizing the displacement value, and also minimizing the surface area of the bridge design. So these three goal values, like more or less, that is minimizing the displacement and maximizing the lowest natural frequency, they go into the same direction of making the structure stiffer. And the third goal of minimizing the surface area of the folded bridge is contradicting those, because it wants to flatten, it make the bridge as flat as possible, and the flat bridge is, as you imagine, of course, very, very weak. Okay, so we have to apply loads. I'm going to apply point loads in the middle of the bridge by using the Karamba loads component. By default, it's set to gravity. We don't want the gravity, we want the point loads. This is also, as I mentioned, kind of it's not unimportant how you load the structure, because the gravity would also, if you just load it by gravity, for instance, if it has lower surface area, also the gravity load is less, which is not really realistic. You have the bridge, usually a pedestrian bridge. If this is a pedestrian bridge, it is governed by the people walking over it and in its vibrations, and the people walking over it, it will always be the same load, right? Same maximum load. On the other hand, you might want to produce this design as a paper model, and this is the scenario I'm going to look at now, where you have a little paper model of a, I don't know, maybe 30 centimeters length, or 40 centimeters length, and you just press with your finger onto the middle of it. So this is what we're going to look at. The point, the middle point is the point with coordinate, is the origin, just finding the point there, and finding the closest points in the structure with the closest points component. By default, it looks at the 3 closest points. We're going to use the 2 closest points. So these are 2, because it's symmetric, it should always find two nice loading points in the middle. The bound points, I'm going to plug into the positions input. And I have to define a force for the loading. So a z vector with a certain value, negative z vector. So we're pressing downwards onto the bridge, onto the middle of the bridge, and plug the load into the assemble models load input. And if we show the model view component, it would actually show us the loads. Sorry, I don't know why. We do have a displacement value, so I can work on that already. Displacement, and label this displacement value as well. Maximum displacement in centimeters, and by default, this is our second goal. Just not sure, to be honest, why it doesn't show. Oh, no, it does. Okay. So, it was a bit too much. So I'm just going to take value a bit less than that. Deforms by 2 meters. So let's make it 2 point loads of 100 kilonewtons each. So this is our loading scenario of the bridge. So to fix it, I just had to place a new shell view. I don't know, to be honest, why this happened just now. Good. I'm gonna change the view settings a little here, placing those 2 loads on the middle of the bridge. All right, and we could just take this now, this maximum displacement value, and optimize with Galapagos again, this single objective, changing the fitness goal to minimize in this case now, and start the solver again, and it will again solve for this one optimization goal. See a number of funny global tryouts already here. But looking at the time, I will just jump straight into the multi-objective setting now. By placing the octopus component. So octopus by now, the octopus original component, it sits all in the octopus tab now. And this is the original multi-objective optimization component. It has a number of other tools by now, which are coming from different research approaches, all revolving around the idea of generative design. First one was the explicit components, which more or less you can redo in just as grasshopper components, and with external looping components like Anemone, you can craft different algorithms or recraft the algorithm of the original Octopus component. And the other ones are components related to machine learning, more or less. So for Octopus, we need all the goal values we want to optimize to be minimization goals. Octopus by default always minimizes, and there's no way to change it inside Octopus from the user interface. So we have the maximum displacement, which we want to minimize, but we have the natural frequency, which we want to maximize. And the simple trick to maximize a value is just to negate it, so to put a minus sign in front of it, and by maximizing this negative value now, we actually, by minimizing this negative value now, we actually maximize the original value. Octopus also connects to genes, and wait, I'm going to hide this. This plug, the G plug, corresponds to the genome plug of Galapagos, and the O plug corresponds to the fitness plug of Galapagos. So with the G plug, I'm firstly going to connect to the 3 gene pools. Also by holding down the shift button again to connect to multiple. So we told Octopus what to change in the setup, and now we're telling it what to look at. And in this case, we're not connecting it to a single value, but to one number container with multiple values. Important is that the numbers always come in the same order, the goal values. And just to have a better overview of what's actually going into this objective, I'm going to use a merge component, our negated lowest frequency and maximum display, and then regular maximum displacement, flatten all those inputs, and just put it into a new number container, which I'm connecting Octopus to. So, and this is this is the minimum setup. We could already double click on the component. The Octopus viewport opens with the 3D solution space window, and our 2 objective rows here, which are just named num, generically named by now, for now. To have more overview of what is what, I'm going to name, to give the dimensions in Octopus names. So the first one is the displacement, the second one is the frequency, and the third one, which we are quickly going to define, is the area. And putting this into a text container, I can connect also by holding shift again, same UI behavior, to this text container. And if I open up Octopus now, it should have taken these names in the 2 objective rows. So the first one is called displacement, the second one is the frequency. The third one, we haven't connected a third value here. I'm just going to take the mesh from before. I calculate its area with the area component and have this as my third goal value. Just connecting this also as a third value to the merge component. So right now then I have here my 3 goal values, all to be minimized. And here are the 3 captions for the goal values. And if I open Octopus now, it should that is a little bug, unfortunately. So if something like that happens, just you might want to either restart. Yeah, in this case, we have to restart Rhino because it crashed. Very sorry. Octopus was and still is a research tool. It's not just not really actively being developed anymore. But as it was a research tool, it was a lot of tries and yeah, different implementations of different features. So there are some bugs here and there. Sorry. I think I haven't saved my run file. I'm just going to take, this is what I meant before. Saving often is very advisable. But it's just, yeah, I'm gonna, those we have the 4 points and we have the bridge setup as we've just, oh, yeah. So here we are back again. I just have to re-reference those points. This is, very sorry about that. Yeah. So here we are. And then Open Octopus now, it has 3 objective rows, displacement, frequency, area. And what I'm going to do, so we have the full setup that I wanted to show you right from the beginning now. I'm going to connect the solution mesh that we have just calculated the area from as the mesh that should be shown in the Octopus viewport. So this is the 3rd input. It's called the phenotype. And with this, by connecting a mesh into there for each solution, like these meshes are shown in the viewport. Okay, so let's see. We can just run it with the default settings. Octopus, what also Octopus does is it minimizes Rhino from the start. When you start an optimization run, you can deactivate that by unchecking this box here, minimize Rhino on start. It just does it by default because usually you want to minimize to have better performance, as said before. Okay, and there we go. While it optimizes, how long should the optimization run? In general, it's a few generations at least, because if you're still within generation number 0 or 1, which you see in the bottom timeline bar, it didn't do much selection at all. So basically, it's just the best of a number of random tries. If you have ran it for a couple of generations, say 5, 10, 20 generations, there is some of the powerful evolutionary logic of Octopus being applied already, and the solutions are much better usually. So let's just see. This looks a bit weird. Let's hope we have connected everything the right way. But the displacement, it's minimizing. The frequency here, it's minimizing the negative value, so it's actually maximizing. And the area, we are also minimizing, so it should be all right. So we're just gonna let it run for a little, and I'm trying to explain you some of the settings here. So the view settings on the top left are kind of important. It shows you, it lets you choose which set of solutions to show. So the history are the yellow buttons. Just gonna hide those for now. Just shows you a trail of past solutions, of past generations, sorry. So this is the actual evaluation pool, the actual generation, the current generation, I mean. And then I can, the radio buttons, the round radio buttons, they let you choose the scaling of the solution space. By scaling to the Pareto front, I'm just showing this Pareto optimal set of solutions. By showing the elite, I'm showing a bigger subsum of the current generation. And then when I input the meshes into the Octopus component in the Grasshopper canvas, it automatically enabled the mesh view. And here with this little slider, I can change the size of the meshes. And if I increase the size a bit, I can already see the different 3D models of the bridges. Okay. Maybe I want to reset the cam. This is in the menu above here. You can say cam and reset. So it's still working. After 12 generations, it should have found something, some solution. This is another window that pops up with Octopus, because you might have noticed the user interface while calculating with Caramba especially is very jammed, is very unresponsive. This one runs on a separate thread, and you can always stop and pause the calculation with it. So we are here. This is our Pareto front now in the 3 goal dimensions. The elite to it, you can, you can here, you have the mesh scale, then the opacity of the Pareto front. You can set the low opacity for the elite, so you can easier identify which ones are the truly best that it found. And right now it looks a bit, a bit biased to one plane of this axis system. If I look at the displacement, it's 003 is the best value it found, and 1920 is the worst one it scales to in the Pareto front now. So there are 2 things I could do. I could just click on this solution and say delete and see what's happening, but for now I don't want to delete anything. I just want to scale the maximum display of the displacement axis to a maximum value, and that's what I can do here by setting it to, let's say, 10. Let's try 10 centimeters. Clicking on this one, and it scales to the maximum of 10. And we have a bit of better distribution of our solutions. So the frequency, it optimized quite a bit more than Galapagos even. We had a maximum of 6.5 with the frequency optimization, single objective frequency before. Area and displacement we haven't really optimized before, so we don't have an idea of where the good values are. But also now we have these 3 performance axes, and we can check the visual side of each design as well. So let's see. The thing is with the runtime, how long should the optimization run? In the beginning, it tries a lot of different random solutions, and the diversity between the solutions is very big. So there's a lot of diverse solutions. If it continues to run, it converges to different kinds of solutions that it identifies as the best trade-offs, and it narrows down the diversity of the trade-offs. So this is one of the trade-offs in multi-objective optimization itself. The better you want to be one design trade-off or compromise, the least other solutions are usually maintained in the optimization. This you can see, for instance, in the graph down below here. It shows you the parameter distribution between the different solutions. If you hover over one solution, it highlights, and you see it's basically all very similar to one zigzag graph already, one zigzag line. If I try now to go back in time, here with the timeline slider, just by dragging it and going back, I see the parametric diversity increasing again. So in the beginning, it was very, very diverse, yeah. And then over time, it found, yeah, it just converged towards a certain kind of solution. And if you look at that, unfortunately, if it's just the last generation that the solutions are saved for, the solution meshes, because it would be just a very vast amount of 3D models to save. Yeah, you have this kind of weird design that it more or less sees as a very, very fit one. The bump in the middle, I think, is mostly due to the fact that we loaded on 2 points, and the 2 points where it applies all the load to should be also stiff in itself locally. So it does this little stiffening of the loading area. That's why the little bump in the middle of the bridge comes up. And the other shapings, they are trying to save. They're trying to create some kind of folding. Okay, let's see what it found, for instance, in, yeah, it's a pity you can't really go back. But now, basically, we're a bit over time already. Found a lot of different here. If you reinstate the solutions, let's just start again and see, and stop it a bit earlier. So I can also do that during the optimization and say maximum 10. Is it nicer? You know what? I'm just going to switch to this now. Finish up slowly. Here we have run it for 6 generations, I think, 5 generations. And it gave a very, very diverse set of solutions of bridges, which are baked from here. So you go in, assess the solution, for instance, that one, and you say reinstate solution. Then it sets the parameters again as it corresponds to those solutions, and you can just bake it into Grasshopper. So you have this design saved. What you can also do is you create a Grasshopper state, for instance, or you can second item in the context menu, you mark it just, so you have a little reminder that you have looked at it already, for instance. To create a Grasshopper state from it, just from Octopus, without going deeper to Grasshopper and to reinstating. I've now created a state, as I've explained before, with the solution from today, this and that time. Yeah. So I can also, I mean, there's many different, and some of them are very experimental features in Octopus. You can, so this is more or less what you usually do. You create those solutions, let it run for a number of generations, check the genetic diversity, and see where you're going with it. And then it's a lot of playing around with the fitness values that you have defined, with the way you have defined your loadings and your parameters, with the mapping of the problem. So it's a very delicate kind of way of working, way of generating designs in a way, or optimizing designs. I like to distinguish between 2 kinds of evolutionary or generative optimization. So one is qualitative optimization, what we've done now, more or less, which is the way harder one to achieve nice results with. So this one where you actually want to create design, where you want the computer to be creative for you. And the difficulty is, if you want a creative output, you have to let the computer a certain freedom, but this freedom actually makes it harder for the algorithm to find good designs on the other hand. And then you also run into the problem of this convergence issue. The longer it runs, the less different design ideas it maintains. The other way of optimization is quantitative, and quantitative optimization is, for instance, you have a more or less fixed or given design. For instance, you have a simple slab and you want to optimize the positions of the columns in certain areas. I can show you one example of a project we have done. This Hyundai Motor Studio in Seoul is a very good example for that. So we have this steel structure, and we want to place the columns underneath it. We had the footprint basically of the roof, and we had a certain area where we were allowed to place columns. And by just letting Octopus define those places of columns, it was very effective in finding different solutions. And yeah, we were able to show the architects, in this case, a set of different column design solutions with a different number of columns. We were optimizing the mass to minimize the mass. We were optimizing the displacement in this case, so to minimize the displacement of the entire roof. And we were optimizing the number of clusters also to have a minimum number of columns. And in the end, they chose an intermediate solution with six column clusters. And this was kind of a hybrid, but I would say more into the direction of a quantitative optimization, where the problem or the design, in the classical sense of artistic or creative design, was already very fixed, and it was just changing some numbers to really just optimize a given thing. And this is the easier way to do the engineering optimization rather than an architectural design creation in a way. Okay, we're a bit over time. I think, yeah, I hope I have given you a little insight of how this works. There is reading attached. You can go through David Ratton's examples. You can also write us if you have very specific questions. If you decide to use Octopus for your design assignment, I would recommend better that you learn to use Galapagos first, to be able to create a single objective solution first and then switch to Octopus. Just because Octopus is more of a, yeah, it's just an extension of Galapagos for more advanced users, so to say. So that's the way to go. Okay, thank you for your attention. Yeah. We can do some questions. I have the next meeting in 15 minutes, so it should.
I have a question.
Yeah.
As the visualization is three-dimensional, so the maximum number of goals we could have is 3 in Octopus.
Yeah, no, I mean, in this visualization way, you still have if you connect the fourth and fifth goal, it adds the coloring of the 3D models or the solution cubes from red to green, and it shows a different legend here. And the size is also another one that it adds. If you go further than that, or in general, you can always switch to the X view by this menu item and the multi-X view. You have this zigzag where each vertical axis is one goal dimension. You can it's actually also just a 3D model, and you look at it.
Okay.
It works more or less the same way. You have the context menu then, and you can change, because like how it is sorted here, what the fattest ones and what the thinnest ones are, is also just a linear sorting, so you can change this a little here. By default, it's trying to have a kind of intermediate sorting, so the trade-off solutions that are close to the origin more or less are shown thickest. Yeah, but I can try. I mean, we could try to add another goal value just to test by feeding in any value here. No, I would have to run some setup, some design. You can actually see how it looks in the presentations pictures of the interface, I think. Yeah. So here on the left, you see the coloring from red to green, and also different sizes of the cubes. And then here we have, yeah, the legend is missing. I think it's an old interface picture. Yeah. So five do make sense. And otherwise, if you have more than 5, you can also switch. In the viewport, you can switch the axis. So I can show all. I can show on all 3 axes. I can show the same goal. Obviously, it will be just a diagonal by changing those buttons here. How you assign or which objective basically you assign to which x. And there's axis 1, 2, 3, color and size. I can switch on the color. I can switch on the color and size just for some of them. If you do all the same, it goes from green to red and from small to big.
Okay.
Yeah.
Thanks. And how does the computer find this pattern, like the yellow curve on the bottom left of the screen?
The yellow curve is just the marked solution. If I unmark it, the yellow curve disappears.
Yeah, but you said that the computer can find a certain pattern to do the optimization. And how does the computer find this pattern?
How it chooses which solutions to produce and which ones to select? You mean?
No, I mean on the left, bottom left of the screen.
Yes.
That the curves it converges to a certain pattern.
Yeah.
At the end, and how does the computer choose this pattern to do?
That's the entire alchemy. That's the big question. How does the computer decide which solutions to converge on, or where to go?
Yeah.
Based on these principles of in the beginning, basically in the first generation, it just produces 100 random designs and select the 10, say about 10 best ones according to the goal values. And then from those 10 designs, it changes those 10 designs slightly by different principles like mutation or crossover, and produces 100 new designs from those 10. And so, and from the 100 new designs, it again selects the 10 best, and like this, it proceeds and continues to improve the design. And then how it exactly arrives at this zigzag line in the lower left is the result of a lot of different factors. So it is your definition of the grasshopper setup. It is your definition of the goal values. It is the algorithm settings here. How much mutation, how much crossover, and so on you want, and how long you actually let it run here. But what I found, it is most important how you define the problem actually. So what goes on in your grasshopper canvas in between the parameters and the goal values is very important to what kind of design it produces.
All right. Thanks.
Okay. If we don't have any more questions, I think we're done.
Yes, I have a question.
Oh, yes, okay.
Just what is the difference between Octopus and Walesi?
Not much, I think. Walesi, as far as I know, I mean, Octopus was just, we were lucky to have that idea and be, as far as I know at least, the first ones to publish a multi-objective optimization tool for Grasshopper. Walesi just came a bit later, and they started, I think, with the visualization toolbox first, and then introduced in a second release or in a further release also the optimization algorithms. I think, I mean, all of those tools that are out there now, the Opossum or the Silvereye, and they do a good job. I think it's just some different user interfaces, slightly different algorithms, and different people that develop them. And but I'm sorry, I don't know the exact details. I think there are a couple of papers that compare the different optimization tools for Grasshopper, like Opossum or Walensee or Octopus. But the exact details I'm not 100% aware of.
Okay. Thank you.
Sure. Welcome. Some new direct. I mean, what we just wanted to have for a while, but which is very complicated in terms of the Grasshopper logic of Grasshopper 1, and I think it will be much better in Grasshopper 2, is just to have, say, because these components as they are now, they corrupt the usual way that Grasshopper works, right? Usually you plug in something, you change something on the left, and everything downstream updates, and those guys just, they hack the Grasshopper logic in a way. And you cannot really have one component, you cannot have this component as part of the setup. So if this component updates the Octopus component, Octopus cannot start by itself, do a fixed number of iterations and give you one good design. You always have to do it manually somehow. So to have this kind of evolutionary solver for many problems that maybe you optimize every single facade panel of a big facade in a special way, just to be a bit better than a random guess. This is not possible so far, and I hope it will be possible in Grasshopper 2. But that's a very technical side. And the other thing that recently I see it going on, at least, is the use of machine learning methods, partly because people just picked up the idea again, because all the hardware developments and so on, they're progressing in the field. And on the other hand, because the algorithms were just developed further and there were more algorithms available suddenly. So the idea, one idea that we had a PhD here in Vienna recently graduate, is to have the evaluation here. For instance, you see that this calculation of the Caramba model, for instance, takes most of the time of the setup. And if you have to do thousands and millions of iterations on that setup, this takes a lot of time. So you could as well use, for instance, for the generation of new individuals, new solutions, you could use neural networks that were trained, that are trained during the run of the evolution to mimic more or less based on the input. You give it an input parameter and it tries to predict the output parameters, and without having to actually recalculate the entire solution, but just evaluate the neural network, you are able to make a better guess maybe already which random solutions that you generate as new offspring are performing better than others. So you can do a pre-selection with machine learning, for instance, or Opossum, I think, uses very advanced mathematical surrogate models. That's the name for what I just tried to explain. To have a neural network try to mimic your Grasshopper definition is a surrogate model, and Opossum, I think, relies quite heavily on different kinds of surrogate models. So this is, I think, definitely where things go. And then the other is visualization. The Design Explorer, I think, by Tomasetti, yeah, they have a very nice web interface just to be able to look at different solutions in much more elaborate ways and very, yeah, just to have this multiplicity, like you have hundreds and thousands of different solutions and you want to have some kind of filtering them sometimes. Yeah, that is what comes to mind. So machine learning, visualization, web interfaces, and maybe also Grasshopper 2 bringing some platform specific improvements. I think Autodesk and Dynamo, they have these capabilities already to have just a bit of more flexibility in how you design the algorithm interface or the integration. Okay. Sure. Also, maybe I'll give you one more input. Something that's really that I read with great interest recently. It's Daniel Davis is an architect from RMIT. He wrote his PhD thesis a couple of years ago, and maybe a couple of you know him also. He was at WeWork for a while, and he's a writer. And the recent blog post of his is this one: generative design is doomed to fail. He dealt with generative design a lot, I think, during his academic career, and now gives the statement why he thinks generative design is very, very is to be syncretical in practical work, but he focuses mostly on architectural design. I would oppose his. I think he's right in many things he says, but especially when it comes to creative design. But for the quantitative design I've been mentioning before, so if you want to just optimize the cost or the structural performance of something, I think generative design can still be a very valid and powerful tool. But that is maybe just the other side of it, to be a bit critical about these automation algorithms that do all the design work for you, as some people think. Okay.